Welcome to the STEM Sessions podcast. I am your host, Jarl Cody. I've spent my fair share of time hiking and backpacking on local trails and in the backcountry. And over the years, I've picked up rules of thumb that help you estimate how much daylight you have left or how the temperature will change as you climb or descend in elevation. And that's just to name a couple of them. But recently, I was introduced to a new one, or at least one that's new to me. In Dave Canterbury's YouTube video published on May 17th, 2023, there's a link in the show notes in the reference section, he shares a rule of thumb for estimating distances between you and a target. And while Dave offers a great how-to explanation for his rule of thumb, his video doesn't explain why it works in the first place. And this caused me to raise a people's eyebrow of uncertainty. It just seemed too easy to be true, and yes, I realize that's a confirmation bias unto itself, but anytime something is presented in a just trust me fashion, it makes me want to prove it myself even more. So that's what I'm going to do here. I'm doing the work to prove or disprove this rule of thumb, so I know if it can be relied upon the next time I'm off trail in the backcountry. This is the STEM Sessions Podcast, episode 23. Thumbing for distance. Despite not having a definitive origin, the phrase rule of thumb can be dated back to the 1600s. It most likely referred to using one's thumb to represent an inch while taking measurements. But today the phrase can be used for any method of approximation. It's typically a method that is easy to remember and is a shortcut to results based on repeated practical experiences rather than application of theory or calculations. We use many rules of thumb in STEM and in day-to-day life, but we rarely ask ourselves why the rule of thumb works. We just assume it's good enough. Why else would it be a rule of thumb if it wasn't correct? Well, I recently learned a new rule of thumb, one for estimating the distance between yourself and an object. It involves extending your arm in front of you with your thumb pointing up. With one eye closed, you sight down your arm and move your arm such that your thumb is either just to the side of the target or in the middle of the target. Then you close that eye and open the other. As you do this, your thumb changes position relative to the target, or maybe it's the other way around. Well, you estimate the number of target widths your thumb seems to have traveled, and you multiply that number by your best guess as to the object's true width. Then you take that quantity and multiply by 10. The result is the distance between you and that object, provided you kept all of your units the same. I'll leave it to you to watch the original YouTube video for a much clearer explanation, but for now I want to focus on whether this rule of thumb is valid or not. Now, the multiply by 10 part immediately struck me as too easy to be accurate. Now, accuracy is absolutely important even in rules of thumb, especially one involving distance to target. So I decided to determine how close that 10x really is. I'm very familiar with navigating trails with map and compass, and plotting a course using triangulation between points is a common tool. But while that's not exactly what we're doing here, I had a feeling triangles and plotting would be a good place to start. So, I pictured a piece of graph paper with me standing at the origin, or point 0, 0. The target would be at point 0D, where D is the distance to the target, the real distance to the target. When I outstretch my arm, my thumb is at point 0A, where A is my arm length, or more accurately, the distance between my eye and my pointed up thumb. When I switch eyes, my thumb moves a multiple N of the target width. That new point is NW, D. When you close one eye and open the other, what you're really doing is shifting the origin point of that line. And you're shifting it the distance between your two eyes. So that new point is going to be negative E, 0. Now, it's negative because it's in the opposite direction that your thumb moves, but you could really just assign whatever orientation you wanted to as long as you keep the overall magnitudes the same. When you look at your sketch, you'll see that it now has two triangles. There's a large one between your thumb, point 0A, to the target, point 0D, and to your projected thumb distance at point NWD. The other smaller triangle is between your thumb, 0A, to your first eye, point 00, and to your second eye, point -E0. To relate these triangles together, we can use the rule of alternate angles. This tells us that the angles converging at point 0A are equal to each other in both triangles. Once we know that, we can use the tangent of the angles to combine all of our variables together. The tangent of the angle is the length of the opposite side divided by the length of the adjacent sides. So in the first triangle, the larger one, the tangent of the angle is NW divided by the quantity D minus A. And in the second triangle, or the smaller one, the tangent of the angle is E divided by A. Again, the negative sign doesn't really matter here because we're just talking about magnitudes. However, the negative sign was important in order to establish the relationship between the triangles using the alternate angles theory. Now we set these two quantities equal to each other and solve for D. The result is A plus the quantity A divided by E times NW. There are two conclusions we can draw from this new equation. One, the results will technically vary from person to person because arm lengths and eye separation distances vary from person to person. And two, as the distance to target increases, the term with only your arm length, that first A term, becomes less important because the second term starts to dominate. Now let's focus on the validity of the 10x multiplier. In the equation we just established, the 10x multiplier is represented or corresponds to the term A divided by E. So the length of one's outstretched arm should therefore be 10 times longer than the distance between your eyes. The distance between your eyes is called the pupillary distance. You'll find it on many glasses prescriptions, though it oddly wasn't on mine, so I actually had to measure. Technically, there are two pupillary distances. One is for near distance and one is for far distance. When you look at something up close, your eyes tend to point inward, and when you're looking at something far away, your eyes more or less point straight ahead. There's a 3 to 4 millimeter difference between the shorter or the near pupillary distance and the far pupillary distance, with the obviously near pupillary distance being the shorter of the two. But it's the far pupillary distance that's applicable to this discussion. The average adult pupillary distance, or specifically their far pupillary distance, is 62 millimeters, with a normal range of roughly 10 millimeters to either side. Pupillary distance can vary between gender and ethnicity and age, so just keep that in mind. The average adult arm length, or more accurately, the distance from your eye to your thumb, is even more difficult to find, if not impossible. But to achieve that 10x multiplier, the distance between your thumb and your eye would need to be 62 centimeters or 24 inches. And that's because the average pupillary distance, again, was 62 millimeters. So you want that 10x multiplier, that 10x ratio. Now, for reference, I measured my eye to thumb distance to be a bit over 23 inches, or right around 59 centimeters. I'm right around 6 feet tall, which is a bit above average for a male. So I would expect my arms to also be a bit above average length. But what this tells me is the 10x multiplier is an overestimate, most likely one established to account for variation in everybody's anatomy. When judging distance, it's actually probably better to overestimate in the first place because there are fewer negative repercussions of overestimating a distance than there are underestimating a distance, especially when travel is involved. Plus, each individual adds uncertainty to the equation anyway because you have to estimate your target width and your thumb displacement. And I suspect people would probably underestimate these variables more than overestimate them. So again, using a larger multiplier then is than what theory calls for is probably there to compensate for all those variabilities in calculation. And again, this is a rule of thumb, so multiplying by 10 is just easier to do in your head. For completeness, my pupillary distance is 64 millimeters, and my eye to thumb distance is around 590. So my personal multiplier is closer to 9. It's approximately 9.2. I plan to run some controlled experiments in the field to see how close this number actually is, and those results will be featured on a future episode. But for now, this exercise has given me confidence that this rule of thumb for estimating distance has some mathematical basis and isn't grossly wrong, and I'd have no problem using it the next time I'm on a trail. Using a rule of thumb blindly is okay most of the time, but there are always exceptions to the rule. Understanding the background and basis of the rule of thumb is critical to understanding when you can count on the rule to work and when it shouldn't be used. Plus, it's just satisfying to know why it works in the first place. Thank you for listening to the STEM Sessions podcast. This episode was researched, written, and produced by Jarl Cody. Here at the STEM Sessions, we strive to share accurate and complete information, but we also encourage you to do your own research on the topic we discussed to confirm the accuracy of what we've presented. Corrections are always welcome. Show notes, contact information, and details of our other activities can be found on our website, thestemsessions.com. If you received value from this episode and wish to give some back, please visit thestemsessions.com/value for ways to support the podcast. Finally, please remember STEM is not a tool exclusive to experts, policymakers, and talking heads. Every presenter is susceptible to unconscious and sometimes deliberate bias, so always verify what you read and what you're told. Until the next one, stay curious.